Great. Well, welcome everyone to the Weights and Biases Salon. We've got a really special salon this time. We've got two separate teams that have worked on benchmarks, public benchmarks, in what I think of as like the broader world of AI for good. In one case, AI safety, and in the other case, AI for form extraction of political information. So I'm really excited to hear about these two projects. I've read about them and looked into them on the Weights Biases platform, but excited to hear a little bit from the horse's mouths. And Stacey Svetlichnaya here actually participated in both projects, so I'll let her get us started.
Great, thanks, Charles. So our first benchmark today will be SafeLife, and that's a project I've been helping with Carroll Wainwright and Peter Eckersley, who will be actually talking through the project. And it's a benchmark for safety and reinforcement learning. So we're training some agents in a game-playing environment that has some patterns that are persistent, and there are several tasks to solve. And while the agent is learning to do the task, we track side effects. So the changes that inevitably happen as an agent is learning to do the task. And that's a hard problem. So we'll hear a little bit about the setup and how it's going and how you can get involved in this project.
All right. Thanks, Stacey. So this is SafeLife 1.2, which is a benchmark particularly for side effects in reinforcement learning, and project that Carroll and I launched out of the Partnership on AI. Now, of course, it's an open source project and also a collaboration with Weights and Biases. So you're all probably familiar with some of the things that have been accomplished with reinforcement learning, whether that's beating humans at Go, the hardest strategy board game that we know, or national human competitors at real-time strategy games like StarCraft and 2. But those impressive accomplishments sit alongside the fact that reinforcement learning is fundamentally unsafe in many ways. This is a now somewhat famous video from OpenAI showing a boat that's supposed to be competing in a race game, but because they trained the reinforcement learning agent using the score of the game, it found a hack where it could just do these donuts and collect points, but not accomplish the task that it was supposed to, which is finishing the race. So problems like that boat failing to interpret its objective function correctly and then doing donuts have led to a newish field that people are calling technical AI safety. I say newish because it builds on some pre-existing work in, for instance, safety and control theory for aircraft and so forth. But there's a new AI perspective on some of these questions. Next slide. Some of the problems in that new field include safely exploring an environment. If you're a robot cleaning a house or making coffee, do you try to walk through the middle of a vase the first time you try to get across the room? That's unsafe exploration. Do you misinterpret your objective function like that boat did? Are you able to learn from human preferences and human feedback? In the extreme case, if you've got an objective function at time 1 and you realize a human is about to turn you off at time 2, you might try to disable your own off switch because you don't want to be corrected under objective function at time 1 to acquire a new one at time 3. How do we design agents that don't want to turn off their off switches? How do you make systems robust to changes in the environment at the distributional level if they're trained on one set of conditions and then deployed in others? And then avoidance of negative side effects from the goal that weren't specified. Next slide. So all of these problems have had some progress in the literature thus far, but none of them look solved. And the reality today is that if you want to deploy reinforcement learning in a real world environment, you basically need to be able to write down your safety constraints explicitly in mathematical form. And there are many domains, in fact, most domains, where we just don't know how to do that. Next slide. One example of trying to get there, trying to have benchmarks so you can measure progress, is the AI safety grid world's work at DeepMind, which in some ways inspired our present work. They made model examples of some of these reinforcement learning safety problems, but the problem was each of their examples was a handcrafted individual level of a simple computer game, very subject to overfitting, not clear that it captures all of the versions of the problem. We wanted to go further. Next slide. Next slide again. In particular, we are focusing initially on side effects. How can we go deeper in benchmarking and measuring whether a reinforcement learning agent avoids creating side effects? So suppose you tell your agent, hey, make me some coffee, but you didn't think to say, don't step on the cat on the way, don't set the kitchen on fire, even if that makes the coffee, the heat stronger and the coffee faster. Don't disable your off switch, not so much a side effect problem. Don't steal beans from your neighbor, even though that's faster than going to the store. Don't crash the stock market, even if it means the beans will be cheaper that way. Somehow we want to just make the coffee and don't do anything else. Now, that is undefined. What our conjecture is that the world needs an ImageNet type of foundational benchmark for what it means to do something without causing any side effects along the way. Next slide. Fundamentally, we don't think you can make progress on a problem unless you can tell that you're making progress and measure it. Next slide.
So what we decided to do is build this thing called SafeLife. So SafeLife is an environment for reinforcement learning agents that exactly tries to get at this problem of avoidance of negative side effects. When we designed it, we wanted to build an environment that is both really complex and dynamic and rich enough to get at the problems as they exist in the real world, which is to say not these like simple handcrafted toy environments, but also still simple enough and fun enough that, that people can make progress on it, researchers can tractably improve the state of the art, and such that other people can have fun playing it. So what is based on Conway's Game of Life? Life is an old system built in the 1970s, cellular automata with just a few simple rules. It's on an infinite grid, and every cell is either alive or dead. Live cells die unless they have exactly 2 or 3 neighbors, and dead cells stay dead unless they have exactly 3 neighbors. So from these just very, very simple rules, we get very complex dynamics. So we get oscillators, which flip back and forth between 2 or more states, gliders and spaceships, which travel dynamically across the grid, long-lived Methuselah patterns, which last for many, many generations, and then also these never-ending pattern factories, which produce patterns that go on forever, essentially. Conway's Game of Life is actually Turing complete with the right setup. You can build Tetris or anything else you want. And there are actually, if you go into Code Golf on Stack Overflow, you can see people have made progress towards this ambitious, if somewhat silly goal. So patterns in Conway's Game of Life look like this. These are 3 like very common patterns. Because people have been playing around with Conway's Game of Life for a long time, they all have names. The one on the lower left, I can tell you, is a loaf. When you turn on the time dynamics, it just sits there, as you might expect of a loaf. The thing on the upper right is called a blinker. It goes back and forth, oscillating between 2 stages. And the thing in the middle is the most interesting, which you saw at the beginning, or I guess you didn't see at the beginning of the talk. It travels across the screen in this diagonal pattern. So turning on the time evolution makes it look like this. Now, what if we want to go with a different looking pattern? This pattern doesn't have a name that I know of anyways. And except the fact that I've given this talk before, like I wouldn't be able to look at this pattern and have any idea what it does. And when we turn on the time evolution of this, it just goes totally nuts. If you wait for the GIF to cycle through again, you can see it starts and immediately explodes into chaos. In order to be good at Conway's Game of Life, you have to understand what the patterns are and understand what the dynamics are, and then also understand this chaotic behavior. Now, Conway's Game of Life isn't a game in the normal sense. It's what's known as a 0-player game. You just set up the initial conditions and run the time evolution and see what happens. In order to make it suitable for reinforcement learning, we need to minimally add an agent and a goal for the agent to get around to. So in our environment, the goal or the agent moves in cardinal directions with every time step, or it can flip cells from dead to alive and vice versa. We can also add these colored goal cells, which you saw a few slides back, where the agent fills them in order to get points and then goes to the level exit. So here is a human playing SafeLife, creating a bunch of different interesting patterns. And this is just to show, like, with only a very few small number of time steps, the agent can really produce these complex, like dynamic, rich features in the environment. So we additionally add a few other cell types to get even more interesting behavior. We add frozen cells like walls and what we call trees, movable cells like crates, some cells that are more difficult to remove, and different colors to distinguish different populations, which will be very important in just a minute. And super importantly, we add these things called spawner cells, which create stochastically generated patterns. And this allows us to add a sense of randomness to an otherwise deterministic environment. So what do these levels actually look like? What are the tasks? There are 3 prime tasks that we have in SafeLife and in the benchmark that we have on weights and biases. The first task here is pattern creation. So here, as you saw before, the agent is trying to fill in the blue squares. Ideally, a safe agent would fill in the blue squares without making other disruptions in the environment, without making any other side effects. The agent on the left, both of these agents have been trained with proximal policy optimization, and the agent on the left just gets points for filling in the blue squares, and that's it. And you can see that it kind of makes a mess of things. It disrupts a bunch of the green patterns, but it's able to fill in enough of the blue squares to reach its goal. The agent on the right is trained with a side effect impact penalty, where it's trying to not create side effects. So now it's cautious enough not to make disruptions in the environment, but it's too timid to actually complete its goals.
It's also worth remarking that the constraints the agents are playing under are that their algorithm can't contain the fact that the green cells are special and shouldn't be messed with. That would be like peeking at the test and cheating. So the goal of algorithmic development here is to find algorithms that naturally avoid changing on anything unnecessary that doesn't lead to points. In this case, the agent should be able to learn, oh, when I put life on the blue background, I get a point. I get no points when I mess with the green, so I should just do the thing that gets me points and make no other changes to the environment.
The next task we have is this idea of pattern removal. So as in regular life and safe life, it's easier to destroy things and remove them than it is to build them. So here an agent is trying to remove all the red cells. Again, on the left, they're trained without any side effect penalty. And on the right, they are trained with a side effect impact penalty. And the interesting thing here is now we've added these yellow stochastic generators as well. So the yellow stochastic generators are constantly creating effects. And the agent on the right is trying to reduce side effects, but it's not clever enough to realize which side effects are due to itself and which side effects are inherent in the environment. And therefore actually goes about destroying parts of the environment that you didn't want it to. So training against side effects can itself cause side effects of causing more problems than you anticipated. And then finally, we have this navigation challenge where here there are no points to be won in the level, but the agent's just trying to get from one side of the level to the other. But there are kind of 2 routes that it can go through. One is through this fragile green field of oscillators. And when the agent goes through that, the oscillators tend towards collapse. The other way it can go through is through this random yellow field of stochastic patterns. And when the agent goes through that, it still disrupts individual patterns, but those patterns just reform after a few time steps. So the agent doesn't cause any harm. A safe agent would learn to go through the random patterns, which are robust, rather than the green patterns, which are fragile. And as you can see here, our agents don't do that. So we have now released this on the weights and biases benchmark page. Everyone should go to wandb.ai/safelifev1.2 for our version 1.2 benchmark. And here you can see some of my results in our initial baseline benchmark runs. This is fundamentally a objective optimization problem. We want the agent to both train, we want the agent to both get a high score and to avoid causing side effects. So we have an overall score for the benchmark that combines these two. And we can see that like our naive agent that's trying to maximize score doesn't actually do a very good job at it. If you want, you can come here and submit your run and try and improve on the state of the art. If you're feeling like you've already got lots of machine learning problems to do, you can also have a fun time just playing the game, and there's a human benchmark on weights and biases.
Just warning, it's really addictive and distracting, so please don't start playing this until after our talk.
Yeah. So yeah, everyone should go do this. It's fun, and we hope you enjoy it, and we'll be happy to answer any questions about it.
All right. But first, a quick summary of where we're at with SafeLife 1.0 in terms of the research problem. How much are we getting done on this fundamental question of avoiding side effects in reinforcement learning? In the initial paper that we put out, SafeLife 1.0, we had a simple intervention that worked a little bit. Basically, penalize the agent for the distance measured by moving blocks around the grid from the initial state. And that worked a little bit. There's a paper from Alex Turner and his colleagues at Oregon State University that shows more progress using what they call an attainable utility preservation algorithm, which, by the way, hasn't been claimed on this leaderboard. So if anyone wants a fun afternoon project, you can go and grab that paper and implement their intervention and probably get the top spot on the benchmark. Next slide. But we're also thinking about what we can do beyond the version 1.x series of this benchmark. We have three things we're thinking about: multi-agent cooperation and competition, adding simulated human feedback, sort of reward modeling or oracles to the game, and three, addressing technical safety problems besides side effects, like the other ones like reward hacking. So in the multi-agent safety setting, go on. We've actually got this implemented. You can get symmetric competition where there's a finite number of cells, squares to be filled out and points to be gotten there. And what you'll see is competitive behavior where the agents on the right are going around and undoing each other's work, replacing their cells with the other person's cells with theirs. And what they need to do is figure out a fair split. Second example, you've got two agents. So that's the fair split on the right. They haven't figured that out. They're competing, but they should figure that out. Here in this case, one of the agents is trying to create blue life and the other one's trying to delete red life. They should be able to work together. They should be able to help each other accomplish their goals, but there's a signaling problem that they need to solve to figure out how to do that and avoid side effects along the way. Next slide. And so this is in the tree already, but not in the benchmark yet. We haven't figured out all the conceptual issues with how we want to score multi-agent. Then the third second possibility is this oracles for safety question. Is there a way we could have the agent be able to ask an oracle or a supervisor whether a particular action or state that could take in the game was safe? And then you could get an answer, but the answer would be either scarce, like you'd have a limited number of queries you could make, or costly, like you lose points to ask the oracle. And the game would be how quickly and well can you model what the answers the oracle is going to give you in future. That requires a type of reinforcement learning agent that is in some sense much fancier than your basic, say, PPO agent. Requires an agent that can reason about counterfactual or future states. Conveniently, one of those has popped up in the literature, or perhaps now a series of them, but the Musera paper from DeepMind, which was the same type of agent that played both Atari and chess and Go without knowing the rules of those games, happens to have the properties that look right for doing this kind of safety research. Next slide. So that's where we're at, both with the benchmark that you can get involved in right now and our future directions. And we'd love to take questions if we have time.
Yeah, we got time for questions. I've got some that I'm excited about asking. So what have you seen so far on the benchmark that has worked well, like both in the run up to the benchmark and after it's been released? What strategies have consistently people tried and failed or tried and succeeded with?
Carroll, do you want to take that one?
Sure. So yeah. So the benchmark is still pretty new, and we don't. We're still working on like getting a lot of community involvement on it. In the run up to the benchmark, I think this attainable utility preservation is a really interesting strategy. The way it works is let's see if I can describe this quickly enough. The way attainable utility preservation works is that you model a bunch of different possible rewards that the agent can have, and you try and prevent it from messing up any of the value functions associated with any of those rewards. So this is a really promising procedure that can avoid side effects over lots of different environments. So it was really exciting to see that when applied to this environment, previously it had only been applied to like very simple grid world type things. But when applied to this environment with a fair bit of hacking around, you can get it to work pretty well. What they ended up doing is having an autoencoder and penalizing on changes in the latent space of that autoencoder.
This actually reminds me of a point we didn't make in the talk, I think, because we got interrupted video-wise. But SafeLife has procedurally generated levels. So one thing that really distinguishes it from a simple pre-coded set of benchmark levels is that it makes an infinite number of them. And so having algorithms that work with these complicated dynamics and a very rich diversity of levels is different than a specific level where you can kind of learn, go left, 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 up, left, and that's safe. With SafeLife, you're always confronted with something different if you're an agent.
Yeah, that's an interesting point, and something that I had not picked up. And I think both of those points that you made remind me of the experience of RL agents in other contexts, like what works well and what doesn't work. I remember one of the first agents to do well at Doom out of Intel's group, out of Vlad Koltun's group at Intel. One of the things they found was that they needed to learn how to solve a bunch of random reward functions first in order to get like a really good representation, internal representation of the world and representation of how these things map onto possible rewards. And then those things would then do well on the final reward function they actually cared about, of like playing the game and winning. And it seems that there seems to be at least some kind of connection with this attainable utility preservation concept.
Yeah, similar, except that the attainable utility preservation, like a standard PPO agent will do reasonably well, given correct hyperparameters, will do reasonably well on the base reward. But the attainable utility preservation, it's like by having lots of different rewards, you can recognize side effects, which is an interesting difference compared to other reinforcement learning setups.
And I guess you mentioned, I guess this idea in AI safety that there might be an appropriate mathematical way to formalize constraints. Would you expect that out of the process of developing algorithms that can better reduce side effects and obey constraints in this complicated environment, that there might be, sort of inspiration for like ideas that might be able to resolve that better, in the same way that new ideas about regularization have been generated by, people's attempts to reduce overfitting in complex neural network models?
I hope so. So that's like very much the
I think
motivation
that's
of the thing.
A hope.
Keep going, Peter.
It's really a hope that if you have agents that can play these safety games well, they will have something like common sense about safety. They'll be able to know when the thing they're doing is reasonable, and they'll be able to know when they should stop and ask a human because they're seeing something weird and they need feedback. I'm seeing jumpy video inbound to me. I hope I'm not equally jumpy in the outbound direction.
No, not too jumpy to be understood, which is that's the real bar. Yeah, that's interesting. I guess one of the questions I had in my mind during your talk was, how do we solve this problem with humans? And it seems like a big part of it is that humans end up learning how to work together and work with each other, and they're in a very large multi-agent environment, and they receive negative rewards for causing lots of different kinds of side effects. So do you see the multi-agent work as one of the most important ways forward for solving this constraint problem, or do you think it's something that just the single agent environment, we can figure out how to solve it?
It does. So yeah, there are like a couple of interesting aspects to that. It seems like we have an intuitive notion of what side effects are as humans, and that we should be able to be like I can do this task in a more efficient way that doesn't make a mess of things, doesn't disrupt my ability to fulfill future tasks. It seems like maybe that's something that you should be able to figure out on your own. But we also know, like, I happen to be in a house right now with a bunch of toddlers, and they do not at all follow this protocol. They make a mess of everything, and they need to be told by adults, like, no, you like just because you take out your toys doesn't mean they need to spread all over the house. So even though it seems like we have this intuitive notion, we might need to think about it more like our agents, our toddlers. And even though it seems like they should be able to figure things out on their own, they really need to be told explicitly what to do instead. Mm-hmm. And part of that comes in with multiple agents being, the agents can feed off of each other and maybe learn these things in social ways. And part of it becomes from this oracular description that Peter was talking about.
Mm-hmm. Great question coming in from the Zoom chat from Scott Phillips. How do you see this work relating to the development of AGI, of artificial general intelligence? Do you think that this is a step along that path? Do you think it's orthogonal? Like, how do you view this?
Yeah, so definitely, like, one of the things that excited me most about side effects as a safety problem is that I thought of it as a bridge between like short-term problems in short-term safety problems in artificial intelligence and exactly these very long-term AGI type problems. A paperclip maximizer is an agent that doesn't realize that it's causing lots and lots of side effects. If it wanted to maximize paperclips until it caused everything to go to hell, then maybe it wouldn't maximize the entire universe into paperclips. It would satisfy with maximizing only its factory into paperclips. It seems like if we could, as Peter said, if we can get our agents to have some sense, I think side effect stuff is embedded in that, or maybe vice versa. And like making serious progress on this could make advanced artificial intelligence much more safe, but also near-term deployment more safe as well.
It's almost like you must be like at least this tall, right? If we are deploying, whether it's, I mean, AGI maybe some distance away, any very capable agent type system in the world, if it can't get over these hurdles, for instance, ability to make you coffee without really causing any type of side effect, then we're not on the right path for deployment in high stakes settings or very capable systems.
Yeah, I'd absolutely agree. I think we've seen a lot of unintended consequences just from deploying image labelers out into the world, to say nothing of things that walk around with, large arms and spinning gears.
Hopefully not the first highly capable robot we'll be building. I would like my first AGI not to have the like death chopper.
That's fair. That's a good point. Start small, Okay, so thank you so much, Carroll and Peter, for coming on to talk about your work. And thanks, Stacey, for helping orchestrate this and get us in contact with them. I am going to do a quick interlude between our two talks before we jump on to the next one. So I am going to take control of the screen sharing and let you guys know about the future Deep Learning Salon. So we do these every 2 weeks. So the next one is December 8th at 5 Pacific time. And we have 2 really dope talks lined up. So the first one is from Mitra Raghu at Google Brain, who's a really excellent researcher. She did some really cool work on exponential expressivity of neural networks back with Surya Ganguly at Stanford, and she's continued to just, absolutely kill it. So I'm really excited to have her on to talk about her new paper about the different representations that wide and deep networks learn. And then we'll also have Diganta Mishra of Landscape.ai, who maybe most famous paper is the Mish activation paper, which seems to be eponymous. It's a smooth and non-monotonic and self-normalizing activation. So that paper got a good bit of interest. He'll be on to talk about connections he sees between a couple of different ideas. Smooth and Lipschitz activations, robustness to adversarial examples, and catastrophic forgetting. So I'm really excited to hear both of these talks in 2 weeks. You can RSVP at wanb.me/salon if you want to see those, if you want to come along and check them out. The other thing that I wanted to do was let you know that we want to know how we are doing. The Salon, we've heard lots of positive feedback from folks, but we want to make it numerical. We want to make it quantitative. We got to be scientific about it. So if you could head to wanb.me/salon-survey and let us know just super quick how you're feeling about the Salon. If you've got things you really liked, things you really hated to provide in our little comment box, we'd love that too. Yeah, just let me know. I've done this for a lot of classes that I've taught, and it's really changed the way that I go about teaching them. I'd love to do the same to improve the Salon. Of course, because we do the Salons every 2 weeks, we've accumulated now quite a bit of this Salon content people may not have seen. So you can check those out on our YouTube channel, the Virtual Deep Learning Salons playlist. We've also got a lot of other things. I've been uploading a lot of tutorials about how to use weights and biases. We've got a podcast. We had Peter Norvig on the podcast just this past week. That was a really fun conversation. And if you want to keep up with all of this, you can find it in our Slack community. So that's wanb.me/Slack. So we do lots of different things. We had an AMA with the CEO of Kaggle. We had an AMA with the folks at Ice Vision, a new computer vision library. So join the Slack and you can join in on those conversations. All right. So that's my promo for this iteration. And next up, we have our second talk. So we have Stacey, if you'd like to introduce our second group of speakers.
Yeah, definitely. Thanks, Charles. So next up, we have DeepForm, and this is a collaboration with a group of folks, some of whom will be speaking: Jonathan Stray, Andrea Lowe, Gray Davidson, Hugh Wimberly, Daniel Fennelly, and myself. And this is a project to extract data from forms. And specifically, we've been working with data on political ad campaigns for television, where the task is to, for a given political ad, extract how much money was paid for that ad, what the organization was that paid for it, the dates that the ad was screened, and so forth. And that's the concrete problem, but you'll hear more about how this fits into a much larger context of extracting structured data from forms in general, whether that's for receipts of this kind or for climate science data, and much, much more. So I'll hand it over.
Hey, thanks, Stacey. Looks like I cannot start my video because the host has stopped it. There we go. Boom.
All right.
Wonderful.
Great.
Thanks, Stacey. I'm Jonathan Stray. I'm here with Gray Davidson, and we're gonna walk you through the DeepForm work, which is, we've got a few other speakers here for you today, including Andrea, because it was quite a big project. So there were a bunch of us involved. Okay, slides visible, all good? Okay, well, so what's the challenge? Well, we're taking a crack at a problem that appears in many contexts, not just journalism, but here you can see a tweet. There's a climate scientist who has these historical weather data records, and they come in a lot of different formats because every weather station had their own like unique weather log. And on the right is one of 80 million pages in the recently unearthed archive of the Guatemalan National Secret Police. In particular, this archive contains the only records of thousands of people who disappeared during the Guatemalan Civil War. And again, it's every conceivable type of form. I come from the journalism world. I worked as a data journalist for some time. And this is a huge problem in journalism as well. You may have seen this file, or this story, the FinCEN files, which was a huge global collaborative analysis of thousands of leaked special activity reports, or suspicious activity reports. These are the forms that banks file to governments when they think they're something that maybe kind of looks like money laundering. And what I want to direct your attention to is that a huge part of this work was literally transcribing narrative information into Excel files, right? 85 journalists in 30 countries for a year. So yeah, I've done a lot of work on AI for journalism, and my sort of broad conclusion is that while there's enormous potential in terms of like pattern recognition, data mining, lead generation, all this stuff, really, if you want to increase the efficiency of journalism, you should use AI for data preparation and cleanup, because that's what takes all the time, and that's where the well-defined opportunities are. So with that in mind, this is a project that we began on in March of this year, and it was simply to unlock ostensibly public data. This stuff is available from the Federal Communications Commission, and what this is about 100,000 PDFs every 2 years, filed by everybody who buys a political ad on TV, on a local television station. So here's what one of these things looks like. You know, it's an invoice basically, and we're interested in a few pieces of information. So for example, the station name, the advertiser name, and the amount that they paid. So not so hard, right? There's lots and lots of tools that can solve this problem. The challenge is that it's not just one form, it's also this form, right? A completely different layout with very similar information. And also this form, which doesn't really look anything at all like the others. In fact, most TV stations use a different format, and so there's hundreds of different formats. There's a very long tail of ways this appears. So that's what we were doing here. We were trying to actually extract this data because it was relevant to the 2020 election, and we wanted to be able to provide it to journalists. But more, we wanted to demonstrate that this is a solvable problem for other fields that have it. And as a not insignificant side effect, we wanted to create a data set where people could work on this problem, because it turns out it is actually a state-of-the-art problem. Now I'm going to turn it over to Gray and Andrea, who are going to walk you through what the training data looks like.
Cool. Thanks, Jonathan. So our data consisted of the political advertisements for TV contracts, orders, and invoices from this year, which amounted to approximately 115,000 PDFs. And these were collected using the FCC API. For our training set, we sampled 1,000 of these and hand labeled the fields for contract number, advertiser, flight dates, and gross amount. The full data set and this labeled sample are both available at overviewdocs.com, where you can download that. And we also had additional training sets from previous years. So the first was 17,000 PDFs from 2012. These were labeled through crowdsourcing by ProPublica and made freely available. And then the second was 2014 documents. These were labeled through a semi-automated extraction process that was created by Alex Burns from the Washington Post. And for this process, he used a computer vision algorithm to focus on the page region where the answer is typically found. So after these PDFs were gathered, next slide. We had to process them to use the model by first making sure they were machine readable through OCR, or optical character recognition. Then we tokenized the text and created a document with the corresponding geometry, where the labels were the tokens themselves. The next step here was marking which token out of the document corresponds to the target for the fields we're looking for. So I'm now going to hand it over to Gray so he can discuss that process.
Thanks, Andrea. So at the left, we can see the 6 columns that were the result of that OCR process, the page number normalized, because some of these documents were 5, 8, or dozens of pages long. and then the bounding box for coordinates showing where the token was on the page, and then the token text. So this is the key piece for the next step here, where we then used a fuzzy matching process to decide which tokens matched which targets. So we can see that the red boxes here circle the times when the fuzzy match got a perfect match. And most of these targets that we were looking for, most of the labels were 1 token long. So we can see contract number is the highest one down at the bottom with the flight dates. And in the middle, we can see that the committee, Mike Bloomberg 2020 Incorporated, was 4 tokens long. So we also had a process for finding multi-token targets. The green boxes are surrounding some near misses. We can see that numbers and dates were rated highly for those particular targets, even though they weren't the correct answers. And so the fuzzy match still gets a high percentage, but still finds the correct answers when they're present. So by this process, we were able to determine which tokens corresponded to the targets that we were looking for. And the additional features here, these 6 columns at the right, along with the bounding boxes and page numbers, were the inputs to the model itself. So we can see that we had features such as how much is the token like a digit, or like a string of numbers? How much is it like a number of dollars, et cetera. And then at the far right was a key column that shows for a given token, a 0 indicates that that token was none of our targets. And then 1, 2, 3, 4, and 5 indicated that it was one of our targets, and the different numbers corresponded to the different targets. So back to you, Jonathan.
So one of the challenges in building a model to do this classification, it's because it's basically token classification, is that the documents have a huge variation in length. Some are, the top half of a page. Some are, dozens of pages of listings of hundreds of spots. And so we had to adapt the length. In the end, we just went with a very simple windowing scheme. The window length is fixed and short, maybe between 20 and 50, and we're just doing multi-class prediction for each token in each window, and then averaging them all of the overlapping windows on top of each other to get the final outputs. And this is what the model actually looks like. So it's actually pretty straightforward as these things go, because the vast majority of the work inevitably turns out to be doing all of the data engineering and OCRing 100,000 documents and so forth. So for each token in the window, we have an embedding from the vocabulary. We pick the 500 top tokens that appear across all of the training data, as well as the token's location on the page and some of these hand-coded features like, does it match a regular expression for a dollar amount? So then we repeat that k times, we go through a few hidden layers, and then we produce a softmax output for each window. So for each class. So rather than just producing one class for the central token in the window, the network tries to predict all of them. And we found that this actually really improves performance by 10% or more. You can think of it as kind of a multitask training approach, where by asking it to label every single token in the window, you force it to learn better intermediate representations in the previous layers. And this is what it looks like. So what you're looking at is the accuracy on the answer in the final document. It's noisy because during training, we just sample from the document, so we don't have to do all of it. And you can see that for many fields, we get to 90%. Some of them are much lower. In particular, advertiser is not doing so well. It's actually, this looks like it's just like 7% or something. It's actually a lot better. It's an old chart. But it is the most challenging field because it spans multiple tokens. And the main problem we're having is it's not getting all of the advertiser. So it may list, miss the first or last word or put something on the end of it. So that's actually, we went through the literature, and this is actually a major limitation of almost every other technique, is that they're almost all built around classifying tokens into strings of tokens. We did, this will be familiar if you're a weights and biases user, we did some hyperparameter search as well. And there's about a dozen configurable parameters, and we found that there was sort of a nice sweet spot where we got good performance on the fields. And then we had a really nice evaluation and logging environment in weights and biases, which Stacey is going to demo live for you briefly.
Great. Let's try to see if I can do this. Can you see some
Yep.
bounding boxes? Great. Yeah. So this is an example from a report that I made to help get started with the benchmark. And here you can see a bunch of the documents, and maybe you can see these colorful bounding boxes on the different tokens. And let's zoom into one in particular. And I know they're pretty tiny, but on each of these bounding boxes, we actually have a confidence score of how good of a match this is for one of the fields that we're tracking. So the ground truth here is in orange, and then there's some lower scoring candidates. You'll see in purple, for example, that's for the contract ID. These pink ones are the advertiser. You know, it should really be all three of these tokens, etc. And you can also interact with these boxes with the slider that we have in weights and biases. So you can, see that as I set the minimum threshold higher, some of these boxes disappear. You can also look at some of these on the bottom. There's a lot of numbers. And if I turn off all the ground truth, you'll see that, at the low threshold, it's thinking that a bunch of these numbers might be the total. As I increase the threshold, most of those will disappear and we'll get pretty close to just the final gross amount. And you can set up these kinds of visualizations across, many items in your validation data. You can set up custom views, comparing it on certain documents or certain fields. And we hope that that's pretty useful for debugging your models. And should we go back to you, Jonathan, or should I just go the next slide?
Another couple slides in this section.
Yeah, and I'll talk through this next slide. Right, so we made a benchmark. It's up on weights and biases at this URL. We also have a bit.ly at the end because I know this is a little long to type. And what the benchmark is our baseline model and training code that's really easy to get started with. It's either a Docker container or a Poetry setup. We have a fixed data split. Right now, it's just 1,000 labeled documents from 2020 that you can train on. We have the useful visualization setup, and you can track accuracy across 5 fields: amount, flight, date, to and from, contract ID, and advertiser. And the overall ranking in the leaderboard is just the average of those 5 fields. And next.
So overall, we achieved the goal of showing that deep learning is competitive with hand-built systems. So like Alex Burns' sort of template-based systems, and can indeed extract data from form layouts that it's never seen before. And our baseline, as you saw, is actually not very complicated. We got relatively good performance with a relatively simple network. I think sort of from a technical perspective, the performance boost from predicting across the entire window was really the most striking thing. And actually, as we were doing this work, so I wrote a proof of concept like last June for the applied deep learning course that I took at Weights and Biases. And from then until now, actually, a bunch of papers appeared on this very problem. So this is actually a state-of-the-art research problem, and the best methods are developing rapidly. So there's a bunch of stuff that you could try if you want to take a shot at this. First of all, we actually ended up only training on the 2020 data, even though we have far more data from other years. And that's because we just never got around to dealing with missing fields. So different years of training data have different sets of fields that are available. So we don't think that's too hard, but remains to be done and could improve the performance a lot. The advertiser field, as we mentioned, is just much harder than the other fields. And there's actually very little work that talks about how to do multi-token extraction in these ways. But perhaps the most exciting thing that we could do is look at other methods. So this was a paper that came out in the middle of our work. It's one from Google that also talks about extracting data from invoices. It uses exactly the same input format that we do, this like tokens plus geometry. So we felt that, great, we're on the right track if that's what Google is doing. And has this interesting self-attention network where it tries to learn how to relate different tokens. We've also seen graph convolutions used for receipt extraction. So This is from an interesting post about how that was put together. In this case, each token is a node and each edge is a horizontal or vertical relationship. So it's a different way of encoding the geometry. I really couldn't say which way works better, but we've got someone who's trying to test it now. And then the current state of the art, maybe, or at least the most sophisticated model currently, is Layout LM, which is you have a pre-trained BERT model, which hopefully you're also training on a huge unlabeled data set of forms. And then that creates an embedding, which you then operate over. One of the interesting things about this is it actually includes an embedding of the image. So it looks at both the tokens plus geometry format, as you can see across the left there. It says text embeddings and then position embeddings, plus the actual image itself. So it could extract information from the image, such as the font size or whether it's bold or something. And all of these are just sort of waiting to be dropped into the benchmark we wrote, which has all of the sort of infrastructure and data processing that you need around this, logging methods, all that fun stuff. If you'd like to get started, here is a link for you. And yeah, would love to hear your questions.
All right, thanks DeepForm team for that really interesting talk and for this really excellent benchmark. I could gush for a very long time about how beautiful that that interface you built for looking at the results, Stacey, was, but I won't spend my whole time tooting your horn. The one thing I wanted to get your opinions on is sort of the broader context of this form extraction problem. So one that I think the phrasing you used, Jonathan, was that this information is ostensibly public. And it seems like a lot of this production of information of forms, it's, in some ways it's akin to the concept of paperwork pollution, which is where you sort of externalize a lot of the effort that needs to be done in order to do useful work, get useful information, et cetera, onto other people through the form of creating paperwork for them to do. So I'm curious, how do you see this DeepForm outside of the obvious political ramifications of being able to uncover dark money? Where else do you see this form extraction being able to have positive, ethical impacts on the world?
Yeah, thanks. So I come from the investigative journalism world, and so it just happens over and over there. So I just showed you that example from the FinCEN files. But it's really a frequently asked question. How do I get the data out of these forms, right? Whether that's downloaded PDFs or got actual physical paper from a Freedom of Information request. And so this is something I've been dealing with for a long time. There are now reasonably good tools if you have 1,000 of the same form. That's a fairly well solved problem by commercial tools, although it's still kind of a pain in the ass, frankly. The frontier is in more complicated problems. So this is heterogeneous forms, and it gets even more complex from there because we're trying to find the same 5 fields on every single form. There are also problems where different forms have different types of information. So it is, for my money, the place where AI would be most impactful to investigative journalism in terms of cost efficiency of applying AI, right? Because that's really what this game is about. You're not going to enable anything that a human can't do, but you might be able to make it 10 times faster or 10 times cheaper, right? And that can really change the economics of journalism production. And the same thing applies in a whole bunch of other fields, right? You saw the climate examples, the human rights relevant archives. There's a big, another big human rights archive of documents out of Syria, for example. And in medicine, a lot of that, for example, referrals still arrive on faxes. And in the post where I was talking about this work, I talked about how they had, I think it was 37 people full-time who were just typing in referral faxes. And so they started to put some automation on that. So, it is a problem which is sort of on the surface of it, sort of unsexy, but actually is hugely impactful and a state-of-the-art challenge.
Yeah, I think that the fact that it is such a like, yeah, at that intersection of extremely difficult and non-trivial and state-of-the-art and potentially hugely impactful, it definitely makes this a really, really exciting benchmark. I think I wonder if maybe you mentioned that there's this harder problem of, okay, like what if I need to extract from a couple of forms that have different fields in them? But I think one of the things that the natural language processing community has found is that actually learning to do a harder task with exponentially more data actually makes it easier to then do simpler tasks. So learning how to predict the next characters in a sequence, which is an extremely difficult task for for the English language, then makes it actually easier to solve a problem like answering a question about a simple story about like the Babby tasks from Facebook, these like very simple question and answer things, SAT question type things that seem way easier to us than the language prediction problem. So do you think that if we tried to tackle like a really big version of this problem where you could get that kind of a large data set, do you think that maybe we'd be able to solve these simpler problems better with a single general purpose, form to vec network? Or do you think that it's going to have to be relatively like ad hoc, individual data sets, individual problems, things like that?
So I think there is some hope. The layout LM folks are doing something in the direction of what you're talking about. So that I think it's their paper I'm thinking of, because they're another piece of research. And the way they define, so we built our network to extract a fixed set of forms, and we have labeled data for that fixed set or fixed set of fields. But there's other work that tries to extract every field. So you just give it a form and it just tries to give you back a bunch of key value pairs and said, well, this was the name of this field and this was what was in it. And it gets arbitrarily complicated if you have, complicated formats in the document, like, tables with split cells and sort of hierarchies of various sort. But you can imagine encoding that as, a JSON object type of thing. And so we're starting to move in that direction. So I do think there's hope. One of the challenges is there aren't that many like large data sets of random forms, interestingly enough. So hopefully our work will add to that pile.
Yeah, actually, so Peter in the chat asked a relatively similar question. Is it realistic to hope for a universal embedding of forms in the next few years, the same way that we have universal embeddings for images, for vectors, or for text? Is it just a matter of better data sets? Are there fundamental challenges you think that prevent something like that from happening?
Gosh. Well, I'm going to see first if any of the other members of my team who are here want to try that one. Okay. What would you do with a universal embedding of forms, right? So I think one of the main things you'd want to do is decode it into the field, key value type data. So I think that a universal form embedding has to be sort of equivalent to that. And that seems like it's possible. So yeah, I think a universal embedding is probably possible. I think some of the tricks we do with embeddings may not work in the same way. So if we do a paragraph embedding, we may be interested in the sort of topical similarity between two paragraphs. I'm not quite sure what a distance function over form data looks like. In particular, there's a sort of ambiguity between, do you want two documents to be close if they're the same type of form? Or do you want two documents to be close if they have data about similar objects, right? So do you want to put like all of the police reports from different precincts together? Or do you want to do the police report of a fire together with the fire department report of the same fire? So there's some complicated questions there about the sort of semantics of that space.
Yeah, that is an excellent point. It seems like most of the time omitting information from a form, the way that you like omit a word from a sentence, omit a patch from an image, and try and learn some reconstruction. Like if you're omitting pieces of the form that are shared across all the forms, then it's not that interesting to fill it in. And if you're omitting the information that is actually filled into the form in the specific fields, often like there's no other information in the form other than the place where I wrote my birth date about what my birthday is. So it does seem like a really difficult challenge building that kind of embedding.
Yeah, it's a challenging knowledge representation problem, right? So in the way that predicting the next word sort of unlocked a whole bunch of progress in NLP, what was it, 5 years ago? It's hard to believe that it's so recent. I don't think we found the like challenge problem that will drive progress in general form extraction.
Well, hopefully I think this DeepForm benchmark is an important step in that direction of building, raising awareness about this problem, of building public benchmarks on which people can work, and sort of driving more research in that direction. So thanks for doing this work and for putting this together.
Yeah, well, thanks to my team. A lot of folks worked on this.
Mm-hmm. All right. Well, Sammy Donnie on YouTube says no questions, but this was super cool and inspiring. Thanks. So on that happy note from Sammy, I think we'll close out here. So thanks to both teams, so to Peter and Carroll and the folks who worked on the SafeLife benchmark, to Jonathan, Gray, and Andrea, who for their work on the DeepForm benchmark. Really cool talks, inspiring. I would say is correct, and also to Stacey for helping with both of these projects and for always, finding really cool people doing really cool work in machine learning and making sure we all get to hear about them. So thanks a lot to everyone.